look at the geometry, which is given in the beam.journal file, so the GOU file, which is quite short. Let's have a look in Trelis. So I'll open up Trelis and show you the file interactively. In Trelis, you can use these journal files. I've already hinted at a few times with the so-called journal editor. You can open it up here, and you have an editor window. So let's open up the given journal file, beam2d, and see how it looks like. It has a set of commands, and we can, for example, copy these commands into the command window here and execute them by hitting enter, and you will see the geometry is created. In fact, Trelis logs all the commands it does in the history window. So if you use the user interface to create geometries, you have the respective commands in the history window, and also Trelis produces some journal files directly in the working directory. These are called history01, for example, .jou. You can later look at them and use them to compose your script files. And then the commands are actually rather self-explanatory. We can do the next command in the user interface. This is surface1 size 0.0125. So let's go to the mesh module, choose our surface mesh, choose the sizing. Say we want the approximate size of 0.0125. There's approximate size, and we want to select our surface 1. We can click mesh, and we should have the same result as running this command. Then the node sets you've seen here, I will create them for the sake of speed by simply pasting them into the command window. And you see we have node sets, L fix at the left-hand side, L top at the top, and L bottom at the bottom. So we will use L top and L bottom to specify our thermal boundary conditions, and we use L fix to clamp the cantilever at the left-hand side. Okay, so much for creating the mesh. Let's close Trelis. Let's open up Oxygen with our input file heatmesh.xml. Here we have our input file for the simulation. As usual, we have the important sections of the material assignment, where we have to specify our temperature difference. So dt is the temperature difference. We define a variable that we will use subsequently. And also note that we have to specify thermal expansion tensor and so forth. In the material file, let's also open that up and have a look at it. So here we have the material named alu. We have specified density, Young's modulus, and the Poisson number. So we have an isotropic elastic material, and we have the thermal expansion, which is also assumed isotropic. And here we also define our reference temperature. This is important since this temperature is used to compute the delta T with the temperature used in from the thermal expansion analysis. And further, we have, of course, the material parameters for heat conduction, which are nothing new. So let's look at the sequence steps. We have one sequence step for the thermal expansion, or for the temperature distribution computation. And here we simply specify a temperature at the top and the bottom of the beam. So this simulation is basically only a temperature interpolation between these two boundaries, since we have a very simple geometry. What is important for the next analysis is that we output the temperature results, so heat temperature at all regions. We need them at the next sequence step. And here we have sequence step 2. We have a static mechanic analysis. We use plane stress state, given here in the subtype argument, to the mechanic PDE. And on the left-hand side, we have L fixed, so we constrain both the direction X and Y to 0. And we assume a right-hand side loading. So the input is thermal strain in the area S beam. So this is the name. And then the input is done via reading results from the sequence step beforehand. You could also do the input by simply specifying a value. If you want to specify a value, you can do this directly in the thermal strain tag. So here, when you specify value, you could directly specify a temperature that is used for the thermal expansion coefficient. For example, you could say y coordinate times 10, for example, and you would have a linear temperature distribution in the y direction assumed. So this, of course, is also possible in CFS. However, for a general problem, you need to compute the temperature field, and you can't specify it analytically. That's why we load the results from the previous sequence step, index 1, and we want to load the quantity heat temperature from the PDE heat conduction, and the time frequency mapping is not relevant since we only have one time step in the static heat conduction analysis. However, if you do something transient, you have to tell CFS++ how to map the time values from the previous sequence step to the time of this sequence step. So that's why we need this time frequency mapping. And finally, we store some results: the mechanic displacement, the mechanical stress, and the mechanical thermal strain as an output. So we can save the input file and run the simulation. Here we simply run CFS without any arguments, and it will then read the respective .xml file. So if we use the job name the same as an XML file name, it will read this base name plus .xml and execute the simulation. So let's run it. You've seen this was a very quick analysis. The two sequence steps have been computed, and CFS has generated the results in the results HDF5 directory, and we can use ParaView to open up the results. In fact, I've already and we can use ParaView to open up the results. In fact, I've already prepared a so-called ParaView state file, sigma xx.pv SM you can find in the template. So let's open up ParaView and load this state file to directly see the output. So with file load state, you can load a previously defined and saved pipeline. So this is what I am doing now. You can use this pipeline on a result file in this state file, or you could also explicitly choose another result file. This is often very handy if you want to actually have the same visualization for different kinds of runs that you've done, for example, with different loading conditions. So let's ignore the error message and look at the result. Let's look at the pipeline first. We have first loaded the result file and then applied a wrap by vector filter. Actually, I want to show you the result file first. Why is the heat temperature not shown? This is because this result is saved in the first analysis step. So we have to switch to the first analysis step and look at the temperature distribution, which is as expected. We have the 20 degrees at the bottom and the 30 degrees at the top of the beam, and we have a linear temperature distribution over our cantilever. So what happens if we apply this as thermal strain? We have, of course, again switched to the analysis step 2, where we do the mechanic analysis, and then the wrap by vector result is active. We have wrapped with the mechanical displacement with a scale factor of 300, so we can see a nice deflection. As usual, as expected, we have higher temperature at the top of the cantilever, which by our thermal expansion coefficient, which is positive, leads to an expansion and a compression at the bottom. So the beam is bending downwards. We can also look at the mechanical stress. Here I'm showing the XX component, so the normal stress in beam direction. And you can see we have a compressive stress at the top and a tensile stress at the bottom, which is caused by the thermal expansion. If we also look at the range of stress values, so we rescale our analysis, we can see that we have very high stress concentrations here at the corners where we have applied the fixed support, which shows us the phenomenon that these artificially created very high stresses from the boundary conditions can have a significant impact on our analysis. So in fact, we should choose a bit more realistic boundary conditions here if this was the main target of the analysis.